In this video, I'm taking up the Chapter 2 challenge word problems. So the first question was, we've done this quite a few times. It's the classic cardboard sheet where you cut the squares from the corners and you make an open top box. So I won't spend too much time with this question, but I will say that we have to reject x equals 20 even though it's a root to the equation, because based on the dimensions of the cardboard sheet, x must be between 0 and 7. So 20 is too big. I can't cut those squares because the cardboard sheet is too small. So that means the two boxes can only be the dimensions I wrote down. And after you write them down, you should really check your answer quickly by multiplying the length, width, and height, and make sure that the volume is 1920 cubic centimeters. Okay. For question 2, I have a box which is being enlarged, and the volume must be greater than or equal to 5,280 cubic centimeters. Okay, so I did the simplifying and I said equals 0. I did it very quickly, but you'll probably need a few steps, so take your time. Don't do what I did. I just did it to save space. F of x equals the cubic. I want to solve the inequality, so I have to factor the cubic. And I realized that after I factored it, I saw a quadratic factor which is giving me complex zeros. Okay, I checked the discriminant, it's negative. So that this cubic, f of x, has one real zero and two complex zeros, which means that when I try to solve this inequality, I only have one value on this number line, okay, that I have to consider, which is the real zero. So the complex zeros, they're not, the function is not going to change signs at these complex zeros, because in order for the function to change signs, you have to pass the x-axis, okay? You have to cross the x-axis, okay, like what I have drawn here. So this is not the cubic, okay? I drew this graph to show you the complex zeros make some weird things happen to the graph because of these complex zeros, okay? But what doesn't change is where the function is positive or negative, okay? So you can have turning points here, you can have turning points somewhere up here, okay? Either or, where the function is positive and negative remains the same. So that's why when you solve a cubic inequality which has complex zeros, you just ignore them. All you do is look at the real zeros. And it makes sense to be negative and plus based on the end behavior. It's an odd degree with a positive leading coefficient, so it has to be negative when it's less than 4 and positive when it's greater than 4. Anyways, with all that said, I am able to tell you what the minimum dimensions of the box is. Okay, all right. Question 3 is pretty much exactly the same as what I said for question 2. I have a cubic inequality, I factor, and then the quadratic factor gives me two complex zeros. So my number line is actually really simple. All I need to investigate, or all I need to use to create the intervals, are the real zeros. I just totally ignore the complex zeros. Now, once again, it's negative when it's less than 10 and positive when it's greater than 10 because of the end behavior of an odd degree polynomial with a positive leading coefficient. Anyways, that allows me to answer the question. Now that I know the solution to the inequality, the stock price is greater than $90 after 2009. Okay, for question 4, I was actually really torn doing this question. I really wanted to do the other way, but it was a little longer, so I showed you long division where the divisor is x squared plus 5x plus 6 and the dividend is the quartic. I showed you that the remainder is 0, so that means the x squared plus 5x plus 6, the divisor, is a factor. Another way of doing it is showing that each individual factor of this quadratic is a factor of the quartic, which means the quadratic must also be a factor of the quartic. So for example, I know, or if I have a number in my head and 4 is a factor of that number and 3 is a factor of that number, 12 must also be a factor of that number, okay? So it's the exact same logic, but instead of with real numbers, we're working with polynomials. So if you chose a factor x squared plus 5x plus 6, you essentially have to prove that x plus 3 and x plus 2 are both factors of the quartic. So let this quartic be f of x, so find f of negative 3 and f of negative 2 and prove that both are equal to 0, which means that the quadratic x squared plus 5x plus 6 is also a factor of the quartic. Okay, n of t, question 5. So prove that n of t is, or solve the inequality when n of t is greater than 18. So this time, your quadratic factor, you have to use a quadratic formula to solve this quadratic factor, or solve for the real zeros of the quadratic factor. So really, the problem begins for students when the quadratic factor is not factorable. You really have to investigate. Will I get real zeros or complex zeros? Don't assume one or the other. Just do the math. Let the math speak to you. So in this case, it's 2 real zeros. So you actually have 3 real numbers, which create intervals on the number line. And then you can answer the question. Okay, so there's my answer. So this function has 3 real zeros. Okay, I know 2 of them are irrational numbers, but nonetheless, there's still numbers. So take a look. Question 6. You want to create your profit function based on the information given. So profit is revenue minus cost. Once you generate the profit function, you want to factor it because you're solving the inequality where p of x is greater than 0. So this quadratic factor also gives me 2 real zeros, but I had to find them using the quadratic formula. So I have 3 real zeros. I use those real zeros as points to help me create intervals on the number line, and then using the number line, I can see exactly when I'm going to make a profit. Okay, number 7. Ooh, the box question. So I have the small box. I manipulate the dimensions to make a big box, and the difference in the volume is 96 cubic centimeters. Then the hard part is really just making sure you don't make a careless mistake here. Expand, collect like terms, simplify, set equal to 0. But once I get to here, and I see that this cubic is factorable, if it is factorable, I'm feeling great. Because the likelihood, the chances of f of x being factorable, if you made some careless mistake here, is very, very, very low. Okay, so once you see it's factorable, you are very happy. You're very likely to have done all this algebra correctly. So to test that theory, if you create some random cubic, okay, and to check if it's factorable, you'll see that it's most likely not factorable. So if you made some careless mistake here, you probably created a cubic which is not factorable, and I would never do that to you. Everything I give you is factorable on the test. So that's my little tip. All right, this quadratic factor gives me no real roots. So there's only one possibility for the dimensions of the small box, which is 2 centimeters by 3 centimeters by 4 centimeters. Okay, question 8. Basically, this was the same as the last question on the remainder theorem homework sheet, I think. You have 2 facts about the remainder, which will enable you to solve for v and w, but you have to do so by using substitution or elimination. Okay, number 9 and 10 are the hard questions. Okay, to be honest with you, I really think only 9 and 10 qualify as challenge problems. Everything else, I don't feel like they're challenge problems. But anyways, number 9 is a problem that students really struggle with. And it's because that the students have a misconception with the fact that the remainder has to be a constant term. No, that is not true, okay? Usually we get a remainder which is a constant term because we always divide by linear factors. Our divisors are always a degree of 1, or 99% of the time. But you have to be flexible. Sometimes you can divide by a quadratic, or you can divide by cubic. So for example, like here in question 4, we divide by a quadratic. So yes, I know that the remainder here is 0, but the remainder could have been a degree of 1. Okay, it could have been a degree of 1 or a degree of 0. Okay, so that is actually very helpful to answer question 9. So for question 9, you're dividing by a quadratic. Okay, this is your divisor, quadratic. So your remainder could be a linear or a constant. So I don't know. So that's why I think the remainder is in the form of ax plus b. Okay, so if it's actually ends up being a constant term, then a will end up being 0. Okay, so ax plus b. So that's why p of -2 is equal r of -2, and this is based on the remainder theorem. Well, you can think of it as you look at the division statement. So p of -2 will make the quotient and quotient, so q of -2 times the divisor evaluated at -2 as well, but the divisor evaluated at -2 will be 0. So all you'll be left with is r of -2, the remainder evaluated at -2. So if you're really struggling with this line, really just write out the division statement. You know what? I'll help you. So p of -2 equals q of -2 times 2 minus 2 plus r of -2. Okay, so that was from the division statement. So anyways, once you're here, you'll be left with this, because 2 minus 2 is 0, and 0 times anything is 0, so you're left with r of -2. So r of -2 is equal to p of -2. That gives me one equation in terms of a and b. Use the other factoid to give me another equation in terms of a and b. Linear system, bam, 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 substitution or elimination. Have it your way. All right, question 10. I love question 10. So if x squared plus px plus 1 is a factor of this cubic, based on inspection, ax plus c must also be a factor. Okay, and then these two must be equal. So I can expand, and I know these are an identity. Okay, so the coefficients of the terms must also be the same. So ap plus c is a coefficient of the x squared term, which must mean it's equal to 0, because there's no x squared term here. And the same could be said here. cp plus a, the coefficient of the x term, must be equal to b. All right, so I create those two equations based on what I just said. I rearrange equation 1 to isolate for p, because I'm trying to prove a squared minus c squared is ab. So I rearrange for p, perform a substitution into the second equation I have here, and just slowly rearrange, and I prove what I set out to prove, which is a squared minus c squared equals ab. QED means I prove what I set out to prove. I've done what the question asks me to do. Okay, but this is just fancy. You might have remembered writing this down last year when you proved trig identities, but that's a really small detail. This is what I'm interested in. Okay, so that was the chapter 2 challenge problems.